this computer. Okay, the recording is starting. Okay, great. Today I wanted to talk about more on derived functors and on derived functors for functors between equivalent adjunction between model categories. And some derived functors. Continue today derived functors. Can you see it on the blackboard? Is it legible?
Yep, we can see it.
Thank you, Garrett. Okay, so derived functors, right? So we were talking about this. Let me start with a reminder. As usual, we were talking about this theorem that if f c to d is left equivalent, that is, we have an equivalent adjunction, left equivalent functor, then the functor f q c composition with q, c q, q is taken the canonical cofavorite replacement, and c, and then applying f functor d induces a functor which is denoted by LF from the homotopy category of C to the homotopy category of C. And the idea of the proof was that we can just use the fact that the homotopy category is a localization and use the universality property. So we just need to see that C takes this functor F composed with Q takes when we I think when we compose it with the functor to the inclusion of D, maybe I should say, it induces this, so the idea of let me just prove this. The main thing there is Ken Brown's lemma, which I wanted to prove today. And so all right, so the proof was to say that the standard inclusion gamma of the category of a model category to its homotopy category, or standard map for a functor to the homotopy category will take weak equivalences to two big equivalences, and therefore it will uniquely extend to the homotopy category of C. So there's a C to C. Here you take the covariant replacement, then F to D, and then gamma to D W D inverse. So I want to show that this functor takes weak equivalences to weak equivalences.
Sasha?
Oh, you don't hear me?
Yeah, but the right side of the board it looks blurry.
Oh, really? Huh.
Maybe if you move it to I don't know.
Oh, I see. It might be because of the
lighting.
Because of the light. Thank you. Oh, I don't know. Does it feel better? I think it's kind of. Well, maybe it's the other way around. It feels like, I think it's the light was coming from
Oh, that one.
from the ceiling lights. I mean, the bricks. The bricks were
Oh,
coming
from
the
that
ceiling
line,
lights.
no, from that window.
Oh, yeah.
No, I think it wasn't from the window.
No, it's from the back window.
Or maybe from the front window, I don't know. Let's see.
Actually,
Sergio.
that helped me.
Sergio, can you see it now? Sergio,
I think it looks better.
it looks
Yeah.
good? Okay.
I think so, yeah.
Actually,
It might have just been the angle, like once you
Okay.
shifted the angle.
Okay.
I don't think so.
all right, good. Okay, thank you, Sergio, for pointing this out. Yeah, so, right, and so the point was that we know that that F sends a cyclic covibrations to a cyclic covibrations. In particular to weak equivalences. And so oh yeah. Yeah, sorry. I should have said yeah, here I should have said two isomorphisms because weak equivalences of D are limited to isomorphism. I FQ sends weak equivalences. Well, I mean, what I but in particular, so it suffices to show that FQ sends weak equivalences, right? And we know that F sends, yeah, because weak equivalences are inverted localization. So F sends a cyclic cofibrations to a cyclic cofibrations. That's what we know because F was F was assumed to be left quillen. So it sends cofibrations to cofibrations and a cyclic cofibrations to a cyclic cofibrations. But now the thing is that it's the fact that FQ sends weak equivalences to it follows from so and that's it follows from the following lemma, which is known as Ken Brown's lemma. Why just to show Ken Brown's lemma. Which says that suppose F a functor from C to T, and C is a monocategory, so it's a new story. And here in this case, we'll be talking about F will be composition FQ. So monocategory and T is just a category. And F is a functor. Suppose which F sends a cyclic cofibrations between cofibrant objects. Oh yeah, actually this will be applied to not just to FQ but gamma cofibrant objects to isomorphisms. So it sends a cyclic cofibrations between cofibrant objects to isomorphisms. So this was true about our functor because F sends cyclic cofibrations to cyclic cofibrations, but yeah, but FQ already F when we activate by F will some cofibrant objects, so this satisfies that, right? So this is applied to this lemma applied to gamma composed F. Then the statement is that then F sends weak equivalences between cofibrant objects. Cofibrant objects. Yeah, I think we'll apply it to gamma. But we'll apply it to the image of Q. So it will be working on the cofibrant objects. Right. I think that we should formlessly apply it to gamma. Instead of the gamma before. Within cofibrant objects, so since we can rules between cofibrant objects, also show this one. So this would tell us that in our homotopy area, then equivalences, set of equivalences by composition of those functors. So now let's prove in browser this. Where? So, proof of that's another demonstration of how the axioms of model behavior is broken. So, we'll start with, suppose that we have F in a cyclic. A weak equivalent between cofibrant and cofibrant object. And here's cofibrant object. What we want to show that the functor f in Ken-Brown's lemma is f of little f. Big F of little f is an isomorphic. So we'll take the sum of f plus its identity on B, and consider this as a morphism from A coproduct B to B. And then we split it factorially by using the factorization axiom of model vectors. So, and factor into a composition of a cofibration C or J and a fibration and a cyclic vibration P from C to B. Then we know that let's discuss the properties of this. So we know that A and B are cofibrant. Therefore, the inclusions, well, I mean, the maps, I sketch them as inclusions, but these are cofibrations. The morphisms from A to A union B, or A coproduct B, which I call IA, is also a cofibration. It's a cofibration. And then also the morphism unB from B to A union B is also a cofibration. The cofibrations. So they are cofibrations because they are coproducts of the identity map. For instance, the first one, the coproduct of the identity map A to A, with the inclusion of 0 to B, and both are cofibrations, and cofibrations are preserved by coproducts. right? And then also what we know is that A coproduct B is cofibrant because we get a composition of cofibrations 0 to A, 0 to A, IA, A to union B. Well, A coproduct B. Cofibrate is a cofibration as a composition, So this shows that a coproduct B is cofibrant. Then what else do we need? Yeah, another composition is if we post-compose this with C, with J mapping to C, then we'll see that C is cofibrant. And the composite is a cofibration. Okay, so it's over here. Okay, yeah, so then maybe. Now we see that they can see it better. Hope you will see it better too. Okay, now let's see. A composed with A product B to C is a cofibration as a composition, and therefore C is cofibrant. Therefore, it's 0. A addition of this also cofibration, so therefore it is a cofibration. Well, I mean, we probably need composition, this composition cofibration. So C is a cofibration. Oh, and therefore, sorry, this is a cofibration, and therefore C is cofibrant. C is always better. The composition of 0 to which is because A is the fibrant cofibration. Okay, so we have lots of cofibrations, and finally, yeah. So I forgot to say that this rejection, that is this map. When we factor it, P, I said it, but I didn't write it. P is with vibration, which is in the cyclic vibration. Okay, now let's write down the following identity. That the identity on P, if we is a pair if we compose P J then I B. Right. So IB is the inclusion of P into A union B. And a product, and then we follow up by composition AJ, which is actually supposed to be F plus the identity on P, but since we applied this to we are composing this inclusion of P, then it's a right. So therefore, we get that since the identity of P and P are weak equivalents, then by the axiom of monocategories 2 out of 3, by the 2 out of 3 axiom, J composed with IB is also really 2 out of 3. MC2 by the axiom MC2. Okay, and then we can apply F. So it's all cofibrant objects, like A, B, well, in this case, B, A, product B, C, and B. Everything is cofibrant. Okay. So we apply F, and we know that F sends acyclic cofibrations, the cofibrant objects, to isomorphisms. And so, therefore, yes, F of identity, that's an acyclic cofibration. Then we well, anyway, F of identity is supposed to be identity. Then it's F of composed with F of J composed with I. So F of J composed with IB is supposed to be an isomorphism because J composed with IB is equivalence, which is a cofibration. Yeah, I should have started. So similarly, we'll need to use that first line. The composition of J with IA is cofibration as well. Right? Similarly, B, the version IB, A, coupled with B, followed by J minus C is cofibration. Then let's study this composition of this morphism from B to C with E. So now we know that it goes this way. It's a result of identity. We have equivalences. Therefore, J is also equivalent. It's also a cofibration. J composed with IB. And then, therefore, by the assumption that acyclic cofibrations between cofibrant objects are sent to isomorphism, this is an isomorphism, and this is an isomorphism. Then we know that F of P, the isomorphism may be inverted, so we know that F of P is also well equal to the identity of F P composed with the inverse. This comes with the F of J composed is an isomorphism. It's invertible. So F of P is an isomorphism. And then we can say that we can play with the composition of P with this composition of I, A, and J. So we write down P, it will be actually very stable. So P composed with I, with J composed with I. So J composed with IB was supposed to be, yeah, J composed with IB is supposed to be F, and sorry, P composed with J is supposed to be F, composed. But yeah, when there is different, it's supposed to be F. It's with IA, yeah, with IA. Already you have P composed with J with IB. Now we compose P composed with J with IA, we get F. For the same reason we're getting identity there, and then we'll do the same thing. So similarly, we get so this F of F equals F of P composed with F of J composed with I. And so similarly, we can prove that F of J composed with IB, with IA is an isomorphism. Is again J composed with IA is an acyclic cofibration. So we already established that it was vibration before, and similarly it's a weak equivalence because it's because of the 2 out of 3 components. And on the left hand side, yeah, sorry, not because of tutorial. Sorry. Oh, yeah, 3. Oh. Yeah, F was a weak equivalence. Yeah, so again, the same total of 3. F is an equivalence. So F weak equivalence and J composed of I. Yeah, and P is F and P are weak equivalences, therefore weak composed of IA. And we know that J composed by is co-vibration, and the fact that F was the equivalence was already given to us. We wanted to say that F sends equivalence to cofibrant objects to isomorphic, so we started with cofibrant objects F. Okay, and then therefore again we have an isomorphic equivalence. But then we already proved that F of P is an isomorphic. This is also a nice. So an isomorphism in the second factor, F of J composed with IA, was by the assumption that it sends a cyclical vibration of F sends a cyclical vibration to cofibrant objects to isomorphisms. So we get a composition of isomorphisms. Therefore, F is an isomorphism. And this proves the lemma. Then we said that it sends weak equivalence of cofibrant objects to isomorphism. Any questions? So it's a little tricky game on the axioms of model categories. Yeah, so this allows us to do derived functors of, to define left derived functor of left Euclidean functor. Okay. Now, similarly, there is a dual. G from D to C. If G is a right Euclidean functor, functor, then its composition with the functor R of T. R of G circling R. On C uses a right derived functor R, which is the same R which is used in both cases. So this R stands for the right derived functor of G, and this goes from the homotopy of T to the homotopy of C. And now here, the D and C are model categories, and we assume that we have a right. So this is the dual lemma that is proven the same way. Or you can just use the previous proof and turn the arrows backwards. So talk about functor between the opposite categories and form by forming the reverse arrows. And so just the previous statement will give you this statement. Okay. All right, now let me do another attempt of the second attempt of the tensor home adjunction, and what one can do there. But before this, let me make a remark, which is actually a simple proposition, which basically tells us we can notice what in this theorem allowed us to construct the right a right derived functor, a left derived functor. So in this case, a left derived. Namely, proposition is that note that if whatever function between model category C to D, which sends weak equivalence between cofibrant objects to object to weak equivalences, then again the composition F Q C maps Q maps takes C to C and F takes C to T induces a well-defined functor between the homotopy categories, which we also call LM. This is the homotopy category of C to the homotopy category of T. And so basically the proof of this is the same, except that we don't assume, we don't need to prove Ken Brown's lemma, it's already given to us. So the only thing we need to check is that weak equivalences are mapped to weak equivalences, but by this composition. But but we can actually apply this to the image of this functor Q, that is to the full subcategory consisting of finite objects, and then we'll have a statement that equivalences are taken to the equivalences. This would induce for us a functor from the homotopy category of C to the homotopy. And so this may be applied to deal with the functor. This can be applied to deal with this example to construct, say, well, what I'm raising what I'm going to talk about right now, but I'm going to do it differently, using actually this proposition or this remark that example the left basically the Tor left derived of the tensor product or R of the tensor product functor of the category of R module. So we'll consider a commutative unit of ring R, and then we'll consider the product. But first, let me set the category until the category of differential graded R modules. Let me use the chain version of it that is bounded below chain complexes of modules. So these are these are complexes like 0, M0, M1, go to the left, right? So dot M1, M2, M1, and 0. So the differential has to be -1, but the gradient is non-negative. So these are the objects of this category, right? And we'll induce the model category structure, the standard one, in which F vibrations surjections in positive space, strictly positive space. This is the simplest model category structure on complexes of chain complexes bounded above, sorry, bounded below. So C would be injections, that is injective chain maps in all degrees with projective functors. Then, right, then in this situation,
So the only degree in which a vibration is not necessarily surjection is 0.
yes. Somehow, I mean, there exists a model category structure in which F is surjections in all degrees, but then co-vibrations are described. They are defined as chain maps which possess the lifting property with respect to a cyclic vibration. Yeah, and Greek equivalences are both quasi. There is also a model category structure in which Greek equivalences would be chain homotopy equivalences. So that's a different structure, but we want that structure because we want true derived functors similar to what we are doing homologically algebra. And so in this case, if you have a quasi-isomorphism of projective complexes, the dot q dot. So when we have a quasi-isomorphism with p dot q dot being projective complexes, we know that it's exactly that means that these are cofibrant objects because cofibrations. So I mean, the cofibrant object is one for which the map, the morphism from 0 to it is cofibration. Means that the quaternion then is just the whole thing, and so it means that the term is projective. Right? So these are projective complexes, complexes of projective modules, i.e. cofibrant objects. Okay, and then if we have a quasi-isomorphism between them, then we know that they are all objects are actually fibrant. All objects in this category, objects are fibrant. Okay? The standard map to the 0 complex, which is a terminal object, possesses this property that it's a surjection in all positive degrees. It's also a surjection to 0 as well. And so we get a weak equivalence. This is a weak. This is a weak equivalence between cofibrant objects and fibrant cofibrant objects, cofibrant objects, and therefore by objects, and therefore by the Whitehead theorem in model categories. Have a weak equivalence between fibrant and cofibrant objects. There is a homotopy equivalence. So let me call it F. F is a homotopy. Well, homotopy equivalence in the sense of model categories. So it means it has a homotopy through a cylinder object. So, but the cylinder object is the standard cylinder object. So it's really a homotopy equivalence. So this is in the sense of model categories. And so it means it's homotopic through at least one cylinder object, but homotopies through all cylinder objects are equivalent. If we have homotopy through one cylinder object, then we have homotopies through all cylinder objects. But if we are talking about fibrant cofibrant objects, okay? And so in the sense of model categories, but the standard cylinder construction. So you take, I think, the cylinder of the identity. Cylinder construction. Cylinder of chains, like for complexes, there's a cylinder, the matrix cylinder construction, there's like cone construction. They all are repeated in the homological algebra of complexes, but it may be done. The standard cylinder, and this will give us usual notion, therefore usual notion. So we get the usual homotopy equivalence between complexes, and we also know that this is a homotopy equivalence in the model category sense. And then we can take, so now let's get back to the functionality of what we derive. This will be here. Now, we get to the function we want to derive. Suppose that M is an R module. And then what we see is that we tensor M to F, no, F is an identity on M to Q M is a commutative equivalence, is a chain commutative equivalence, and also a commutative equivalence in the sense of model categories. And therefore, it's a wicked. Therefore, it's a quasi-isomorphism. It's quasi-isomorphism. And yeah, we didn't need to know that to check that it's the sense of model categories. Yeah, it's enough to know that we have a chain component, know that it's quasi-isomorphism. We can use an isomorphism with homology. And so what we've checked is this condition that thus tensor that it's tensor over R, tensor with M, a quasi-isomorphism between cofibrate, a weak equivalence between cofibrate objects. Now we can do it sense takes results in a results. Therefore, by the previous proposition, this function tensor over R with M may be as the left derived as the left derived function. L, this is tensor L on M and X. Yeah, and as usual, we take a cofibrant replacement of a complex. So M first you take a projective resolution. Resolution, also known as a cofibrant replacement. And then, so this will be quasi-isomorphism. And then you apply the tensor factor, we get theta. And this is exactly the derived functor, what you know is the derived. So this relates to the standard construction of the derived functor. And I guess that should be it for today. Questions? Okay, now the sun is out and the snowstorm is over. And the weather is as nice as usual in Minnesota. So I will see you guys. Have a great weekend. I will see you guys on Monday. Oh, and Friday. Friday. Yeah, I'm mixing it up with other class when I teach Monday and Wednesday. Yeah, but I will see you on Monday because it's a break. I'll see you on Monday after the break, but before this, I will see you on Wednesday. Sorry, on Friday.
Thank you, Sasha. Have a good day.
Thank you, guys. Okay, stopping the recording.